Hey everyone, Simplified Engineer back here. Today we're looking at another problem for fluid dynamics. This problem is a reservoir pump station where we have a lower reservoir with a pump that is moving some water up to an upper reservoir. We have a flow rate of 0.05 meters cubed per second and head loss of 8 meters. And our upper reservoir is at 20 meters with a 20 meter height on it. We should also note that our pump efficiency is 70%. So the first thing I'm going to be doing here is looking at the extended Bernoulli equation. And I just sped this up a little bit here so you don't have to watch me write it out, but you should have this basically available in your fluid dynamics textbook. So we're going to look forward to canceling some things out here. The first thing is the pressure. The pressure 1 is atmospheric, and so is the pressure 2. So we can cancel those out on each side of the equation. The velocities are going to be equal to about 0, and this is because the reservoirs have such a large surface area. Even with the flow rate of 0.05 meters cubed per second, it doesn't really equate to any sort of velocity. They are negligible in our equation here, so we can go ahead and cross those out as well. And gravity is also equal, so it's going to cancel those equations out. Even though velocity is 0, it works that way. Z1 is going to be 0, our base, and our Z2, our new height, is 20 meters. So we can cancel out the Z1 here. And then we're going to be looking at our rho, which is basically essentially density of water. I'll get into this later on in the equation, but that does not change in here, so we can cancel those out as well. And we can rewrite our equation. So the head pump, or the head pressure of the pump, is equal to our new height, Z2, plus the head loss. And if we go ahead and plug that in right here, Z2 is 20 meters plus our head loss of 8 meters. We come out to 28 meters for the head pressure on the pump. We're next going to be looking at the ideal fluid power. P ideal is going to be equal to rho times Q times HP, which is the head pressure of our pump. And rho is going to be equal to the density times gravity of the water. And like I said before, this is essentially density of water, but it's the specific gravity. So it's going to be 1,000 kilograms per meter cubed, which is our density of water, times gravity, which is 9.81 meters per second squared, and which means our specific density here is going to be 9,810 newtons per meter cubed. Q is the volumetric flow rate, which is 0.05 meters per second cubed here, or 0.05 meters cubed per second. In our pump head, which is HP, is 28 meters, which we already decided from before. So P ideal, once we plug in here, is going to be 9810 times 0.05 times 28 meters. And that's going to come out to 13,734 watts, or 13.734 kilowatts. All right, so the next thing we're going to be looking at is our P actual, and this is our P ideal divided by our efficiency of the pump. And our P ideal, like we just came up with, was 13.734 kilowatts. And this is divided by the efficiency of the pump, which is 70%, or 0.7. And this comes out to 19.620 kilowatts. And that's going to be the overall power required for our pump to move this water from the lower to the upper reservoir. And that's all for today. Hope this problem helped you out with your studies. If you could drop a like or leave a comment down below, or even subscribe, that helps me out a ton to bring new videos to you. Or if you have any recommendations for anything else you'd like to see, please let me know. I'd be more than happy to help.